progress. There we go. Just going to talk about various drug molecules that we're interested in. We'll talk about how they work, what their side effects are, and then maybe what some of the societal concerns are. There's so much we could do here. We're just going to do what we have time for, and then what we don't have time for, you can learn about on your own. So the first that we want to talk about is really a world-changing molecule called the beta-lactam antibiotic. So one of these, there's a ton of these. One of them is called penicillin F. And penicillins were discovered in 1928. So that's not quite 100 years ago. A little bit when President Nelson was 3, it was discovered. And it's really changed the world. Beta-lactam antibiotics have changed the world because prior to this point, bacterial infections could easily become fatal. And now with antibiotics, we can treat them, though, as time's gone on, bacteria have started to become resistant to some of these, and that's an ongoing problem. But now you have better options. Before the antibiotics, if you were sick, you just sort of had to lay around and hope for the best if it was bacterial and hope that your body could fight off the infection. Now we've got some assistance. So how does this work? The phrase beta-lactam refers to a core structure that is in common among all the beta-lactams. And so if you can recognize this structure, you can look at a molecule and say, that molecule is a beta-lactam, and it's likely an antibiotic. And it's very simple. It's a 4-membered ring. One corner of the ring is a nitrogen, and the other corner of the ring is a carbonyl. And that's an amide bond. Lactam is the word for a cyclic amide. And the key feature, normally we would say that amides are level 3 in terms of reactivity. But the cyclic amide is actually more like the beta-lactam. The cyclic amide is actually more like level 2 because of something called ring strain. So, and I haven't finished drawing the structure. Oh, and I also didn't explain why it's beta. So here's the carbonyl carbon, here's the alpha carbon, here's the beta carbon, there's a nitrogen on the beta carbon. A beta-lactam is a 4-membered ring with an amide in it. And if you draw a square that's a perfect square, the internal angles of the square have to be 90 degrees. But sp2 carbons prefer to be, sp3 carbons prefer to be 109.5, and sp2 carbons prefer to be 120. So the shape of the square constrains all the atoms in this ring to adopt angles that are too tight. And if you tried to build a model with your model set, you would be able to complete the 4-membered ring, but some of the bonds would bulge, and if you flicked it too much, it would pop open. So the ring strain associated with this 4-membered ring makes the amide bond more reactive. So in penicillin F, there's some other things also attached to the ring, but the key sort of warhead part of the molecule, the part that matters the most, is the 4-membered ring. So there's usually some kind of carboxylic acid side chain here, and then there's usually, for beta-lactam antibiotics, there's usually some other chain here. If you were to go look this up on Wikipedia, they would just put an R group on that nitrogen because it varies. Let's see. Yep. 1, 2, 3, 4, 5. But this is the structure for penicillin F. For other classes of beta-lactam antibiotics, they'll have some variation. For example, a commonly prescribed antibiotic is amoxicillin. I don't know how to spell that, amoxicillin. If you take your kids to the doctor with an ear infection, one of the things they'll often prescribe is amoxicillin. It'll be formulated in some kind of pink syrup that tastes okay. And it's almost the same as penicillin F, only the R group is different. Trying to get it right. There's the R group here is an amino acid. It's not exactly tyrosine, but it sort of looks like tyrosine. It's one carbon shorter. That's amoxicillin. And then there's a class of related antibiotics called cephalosporins. These also have the beta-lactam functionality, and they also have a side chain on this amino group. For this particular cephalosporin, it's kind of this weird sulfur-containing ring. This is called cephalotin, and instead of having a 5-membered ring fused to the 4-membered ring of the beta-lactam, cephalotin has a 6-membered ring sulfur-containing side chain. And there are a lot more variations of these. COOH, by the way, is just an abbreviation for a carboxylic acid. There are other versions of this, but they share the same basic core structure, the same important part of the molecule, and that's the beta-lactam, which we're going to highlight in pink. That's the key functional group, and all of them share this. All right, so how does that work? What's their target? What do they inhibit? The target for, and so the core structure you will need to remember and recognize is the beta-lactam structure. If you see a molecule that has that structure, chances are it's a beta-lactam antibiotic. I don't need you to memorize the structure of penicillin F or amoxicillin or cephalotin. I don't need you to know the difference between a penicillin versus a cephalosporin versus some other kind, but I do need you to recognize the beta-lactam. The target is called, oh, that's not meant to be a beta. The target is bacterial cell wall synthesis. So we don't have a ton of time to talk about this in as much detail as I would like, but there are enzymes required for bacterial cell wall synthesis that make amide bonds, okay? And these enzymes have a key serine amino acid. Almost, perhaps you could think of it as part of a catalytic triad, but they have a key serine amino acid that's responsible for bacterial cell wall synthesis. And what happens, we'll just give you a brief example of this, is that the beta-lactam antibiotic effectively acts as what we would call an acylating agent. It gets in the enzyme active site instead of what's supposed to be there, and it is a tempting target for the serine as a nucleophile. So a base in the enzyme active site will remove the proton. That will attack the carbonyl carbon, generating a tetrahedral intermediate. At this stage, we're going to just abbreviate as much as we can to avoid being confusing. So we'll put an R group there, avoid being confusing. You're like, good luck, pal. Another R group here, NH, another R group there. That's the key beta-lactam functional group. I've just abbreviated all the R's, and I'm sorry for that. This is the key enzyme-linked serine. Electrons will kick down and break, importantly break, the beta-lactam and protonate the nitrogen as it leaves. And the product after that now has that key serine side chain involved in an amide bond with the rest of the beta-lactam antibiotic. In other words, the beta-lactam antibiotic irreversibly acylates a key serine residue in the active site of the cell wall synthesizing enzyme. So if you want to see a picture of what this looks like, I looked one up in the protein data bank earlier today. This is just a snapshot of the active site. We'll make it, we'll zoom in on it so you can see. Here is the key serine amino acid. In the enzyme active site. Here is the carbonyl carbon. Here is the alpha carbon. Here is the beta. Sorry, I'm getting that wrong somehow. No, this is the beta carbon, and then this is the nitrogen that used to be in the beta lactam ring. These are R groups on the beta carbon on the nitrogen, and this is the R group on the alpha carbon. You can ignore what's over here. You can ignore this portion. The key portion that used to be the beta lactam is here in pink. You can see how it's no longer a four-membered ring now. It's opened up, and you can see how the carbonyl carbon is attached to the serine side chain hydroxyl as an ester, and that shuts the enzyme down. And if the enzyme can no longer synthesize bacterial cell walls, bacteria get leaky, they're more easy for your immune system to kill, the bacteria die. Okay, other questions about beta-lactam antibiotics? Target is bacterial cell wall synthesis. Yeah, go ahead.
So are the beta-lactams not always the closed square?
They are always a closed square until they do their work on the enzyme, then they open up. Yep. Other questions? So maybe let's talk, the desired action is death of bacteria. The mechanism is inhibition of bacterial cell wall synthesis. So maybe we should also talk about side effects. So some people are allergic to penicillins and penicillin derivatives, beta-lactam. So if you are, your physician will prescribe a different antibiotic. They can mess with your gut microbiome. So my son Adam, I don't know if he's allergic to penicillin or amoxicillin or whether it just messes with his gut microbiome, but he took amoxicillin as a baby and the consequences were disastrous. Like we're talking blowouts, leaky, smelly stuff. There are words that I don't want to say in a class. But anyway, it can have some, and it's not everybody, but it can have some gastrointestinal issues. There's also, beware of allergies, also beware of GI issues. And then a big issue societally is antibiotic resistance. And this is a topic that's really important, especially for those of you who are going to be working in healthcare settings. One of the best places on earth to acquire a bacterial resistant infection is in fact a hospital. And the idea is bacteria, when you put selective pressure on an organism, you can favor organisms that are able to resist whatever you're trying to do to kill them. So there are a couple of easy strategies that bacteria have developed. Number one is to hydrolyze the beta-lactam before it ever gets to the bacterial cell wall synthesis enzyme. So there are enzymes that are called beta-lactamases whose job it is to hydrolyze the lactam, and then it's just a useless molecule. Other bacteria have what are called efflux pumps. They can pump drugs outside themselves before they can do their thing. And there's this sense that if physicians overprescribe antibiotics, especially for unnecessary cases, that you will give bacteria increased opportunity to develop resistance. And there are many strains of bacteria that are now resistant to a lot of beta-lactam antibiotics, which means we have to use antibiotics of last resort that attack via other mechanisms. But if then bacteria get resistant to those, you can envision a world where we all start dying of sore throats again. And that's not a good world. And so physicians are trying to do their part by limiting the prescription of antibiotics. Another cultural and ethical issue is that antibiotics are widely used in the livestock industry to increase weight of like chickens and beef, not because they're infected with anything, but because the side effect of antibiotic administration in livestock is they get bigger. And that produces more meat, but also deploys the antibiotics in a situation where they could generate resistance. And so there's talk about all of that. Other questions or issues you've heard of about the beta-lactams? Yeah.
So what about if you were to start taking a medication and you're supposed to be consistent with it, and then you stop taking it and then you start again? I've heard sometimes you can almost develop this, I forget what it's called, but your body somehow now resists that medication if you go back to it.
Yeah, it's the same thing as developing antibiotic resistance in a community, only it's locally in your body. Imagine you have a population of bacteria in your body and you take a few doses of antibiotics, and after 2 days, 80% of the bacterial population that's bad is gone, but 20% remains. If you stop taking antibiotics at that point, it is possible that the 20% that remains because they are somewhat resistant. They weren't the first to die. Now they get all the resources, they grow, they expand, and the fear is that you will evolve your own resistant bacteria. So that's why it's important for patients to take the complete course of bacteria so you kill everything, so that the last stragglers that are the most resistant don't survive and found a new dynasty of super resistant bacteria. Okay, others? Oh, and this is why, I mean, if you go to the doctor and you're like, I have a fever, my throat is sore. In the past, they would, in many cases, they would just prescribe you the antibiotics and not bother to check whether it was bacterial. Now they'll swab your throat and do a culture, and if it's not staph or something they know, they'll say, sorry pal, it's viral. Antibiotics aren't gonna do you any good. Here's some NSAIDs. And that's a segue to our next drug topic. So let's talk NSAIDs. There's another class of antibiotics called sulfa drugs. Maybe we'll come back to them. I think they were developed about the same time as penicillins. Both of those likely saved thousands of lives in World War II. Okay, but let's talk the NSAIDs. So NSAIDs stands for what? Just stands for NSAIDs. It's recursive. No, non-steroidal anti-inflammatory drugs. NSAID. So you can fight inflammation a couple of ways. There are some steroids that are anti-inflammatory, and there are other drugs that fight inflammation, but they're not steroids. So these are the NSAIDs. Classic examples of NSAIDs are aspirin. So this, and the structure of these is quite simple, and you could probably ask a sophomore level organic chemistry class, based on what they had learned, can you make this molecule? And they'd probably be able to do it. It's got a carboxylic acid here and an ester here. Its non-trade name is called acetyl salicylate. When the ester is gone, it's called salicylic acid. It's derived from a natural product from willow bark, or an herb or a plant called meadowsweet, and people have been chewing willow bark for a long time to treat pain, and it's because the salicylate, the salicylic acid portion of the molecule, which is just this portion without the acetyl group had some pain relieving effects. Another word for pain relieving that you'll hear is analgesic. Analgesic means pain relief. So NSAIDs are analgesics. That means they prevent pain. It turns out that aspirin was invented by a German company called Bayer, I think. And it's tolerated much better than just salicylic acid. Salicylic acid has this cloyingly sweet taste, and if you gave it to patients, they just couldn't tolerate it. It wasn't worth the pain relief wasn't worth the pain of eating it. So they were able to formulate this acetyl salicylate in pills. Other examples that have come along since then include ibuprofen. And the ibu in ibuprofen stands for, I think we talked about this earlier when we were talking about chirality. It stands for this 4-carbon group, 1, 2, 3, 4. That's called an isobutyl group. Like aspirin, ibuprofen has a benzene ring and a carboxylic acid. They make ibuprofen as a racemate, that is both R and S configurations. They'll make a 50-50 mixture of both enantiomers. One of them is active, but the one that isn't doesn't matter. And then the last one is, the Brits call it paracetamol, and we call it acetaminophen or Tylenol. And that's also simple, also a benzene ring, has an OH group, and then a nitrogen there. And these are sort of the 3 most common NSAIDs, though there are others. The mechanism of action for Tylenol is a little bit controversial. That is, they're not totally sure, and there are people that have done research that suggests that it's multiple mechanisms of action. Though for aspirin and ibuprofen, these are called cyclooxygenase inhibitors. There are COX-1 and COX-2 enzymes. These are called cyclooxygenases. And so what do cyclooxygenases do, and why does inhibiting them relieve pain? So the COX-1 and 2 enzymes are involved in something called prostaglandin synthesis. We didn't get a chance to talk about prostaglandin synthesis, so I just want to show you some prostaglandin structures from Wikipedia. Prostaglandins. Blah, blah, blah. There we go. So this is an example of a prostaglandin. That's prostaglandin E. The term cyclooxygenase refers to making of this ring, and it involves oxidation. So you make the cycle and it's oxidation. Here's another prostaglandin. They all come from the same precursor, which is a fatty acid. And they're maybe going to show it to us here. No. Anyway, the enzyme pathway shows you that COX-1 and COX-2 enzymes take a fatty acid precursor called arachidonic acid, and they turn it into any number of prostaglandins. They have different names and different functions, but broadly they're involved in pain and inflammation. Though some of them are involved in stomach acid secretion, and some of them are involved in platelet aggregation. And so taking NSAIDs can have side effects related to these things. So we could talk about the biology more, though we're sort of at the limit of what I personally know about stuff. So what you need to know is that NSAIDs target COX-1 and COX-2 enzymes, and thereby inhibit prostaglandin, which I'm going to abbreviate as PG, synthesis. And the desired outcome, what people hope when you take these, is if you limit prostaglandin synthesis, you will limit inflammation, you'll limit pain, you'll limit fever. Some of the side effects, however, can be and sometimes these side effects are actually desired. So you're going to limit platelet aggregation. So that can lead to undesired bleeding. Go ahead.
Is that why some people take aspirin by cycling?
That's right. Some people take a small aspirin. They've encouraged people to do this for a long time as a blood thinner, meaning it's going to inhibit platelet aggregation as a way to inhibit heart attack and stroke, which often involve, at the late stages, just before everything goes south, massive aggregation of platelets. Yep. Good. Another undesired side effect, if you've got too many of these, as I've said, some of the prostaglandins inhibit gastric acid secretions, so you can get an increase in gastric acid secretion and thereby damaging your stomach. You can sometimes get ulcers. Acetaminophen, because its mechanism is different, it is a pain relief and fever reduction, but it doesn't really do a lot for inflammation. It doesn't really do a lot for gastric acid secretion. It doesn't really do a lot for, I think, platelet aggregation. And this is why I think if you are pregnant, they will recommend for pain relief you take only Tylenol, as opposed to using something that could otherwise cause potential bleeding issues. Okay, and I wanted to show you how it works. This one's really cool too. It's quite similar to the mechanism of action of beta-lactam antibiotics, that is enzyme acylation. So I'm going to see whether we can do this on the iPad. We're going to go to the protein data bank. This is a data bank of protein structures. You can download the coordinates and visualize them in any number of programs. If you're lucky, they will have already visualized the protein for you so you can see the three-dimensional structures. So this is a crystal structure of a prostaglandin synthase, one of the enzymes involved in prostaglandin synthesis. And nope, it's not going to want to do that. Let's see. I'm going to have to do the thing where I stop the video temporarily to bring up. Oh, now it wants to download. Okay, well, that's even better. This is the cyclooxygenase enzyme. And we're zooming in on a portion of the molecule. This is, I told you that the substrate of this enzyme, the way this enzyme works is it binds a long chain fatty acid. So there's actually a tunnel in the middle of this enzyme that the fatty acid is supposed to sit in. Aspirin gets in that tunnel. You saw the aspirin structure. Here is the 6-membered benzene ring, the OH group. This is the carboxylic acid. This used to be involved in an ester, but if you look here, the acetyl group from this ester is right here on a serine side chain. In other words, the aspirin has transferred its acetyl group to a serine side chain in the enzyme active site. And that again damages the enzyme function, prevents it from making prostaglandins, which limits pain. Ibuprofen also binds in this same site in the cyclooxygenase enzyme, but it does not acylate the enzyme. That is, it doesn't transfer the acetyl group. Some of you may be looking at this orange atom here and saying, what is that? That's probably a bromine atom. it's a trick of X-ray crystallography. If you use bromines in some places, it can make it easier to get data on the molecule. So you can ignore this and just see these two atoms here as being originally from the ester from aspirin that would have been here. All right. Other questions about NSAIDs? Sometimes taking too much Tylenol can cause liver damage, so you want to pay attention to the daily max dose for acetaminophen or Tylenol. Also, just physicians will tell you, nurses will tell you, for pain relief, you can alternate Tylenol and ibuprofen. Their mechanisms are different enough that you can alternate them without risk of overdose or any particular problems. So, and that's often preferable to taking opioids because these particular medications are not addictive. Okay. Anything else there? Okay. You got an exam. I'm prepared to talk about estradiol and progesterone derivatives and sulfa drugs today, but I think we're just going to call it good. We'll leave all of that for Monday. May the force be with you on your exam today. Enjoy the break tomorrow. Come to this room, and Myler and Maggie will administer that on Friday, administer that ACS exam if you want to take it. If you don't, that's fine too. And then I will see you on Monday for our last class.